This is RD Sharma solution, class 12, chapter 5, Algebra of Matrices, exercises 5.3. Now, if A is this matrix A to the power n, we have to prove that this is this matrix for all n which is belonging to the capital N, which is the natural number. So, wherever alpha is there, you see there is n alpha. So, we'll do it using the mathematical induction. We have already seen some questions like this. So the first thing which we do in the mathematical induction is we prove that it is true for n equals 1. That is, in the place of n, put 1. That is, you want to have A. You want to get A. So I am taking A to the power of n, putting n as 1. So wherever n is there, put 1. So you get cos alpha, the sine into 1 into alpha, root 2 sine n into, that is 1 into alpha, then minus root 2 sine into 1 into alpha, that is sine alpha, and cos n is 1, so cos alpha minus sine n is 1, sine alpha. Okay, are these two equal, A and A to the power 1? Yes, absolutely equal. That is, the first step in the mathematical induction is done. Now coming to the second step. Here we assume that this is true for all n equals k. We assume it to be true for all n equal to k. Okay. So just put k as n as k. So cos k alpha, wherever n is there, put k. Cos k alpha plus sin k alpha, then minus root 2 sin k alpha. Then we have root 2 sin k alpha. And we are replacing it by k. So cos, again in place of n just put k alpha. So cos k alpha minus sin k alpha. Okay. Now the next step is we have assumed that this is true for any n equals k. We have assumed it. This is true. Now we come for we want to prove it that if it is a to the power k plus 1 holds. If a to the power k plus 1 holds, it will hold for any value of n. Okay. So what do we do? How can we write this a to the power k plus 1, a to the power k into a to the power 1, a raised k into a raised 1. That is, essentially we have to multiply this second with 1, the second with first. So we are multiplying these two now. I hope I am writing this a raised 1 here, the red one, and I am multiplying it. So I am writing directly. So this is the multiplication of a to the power k, a raised k into a raised 1. So first row of the a raised k and first column of a1 I am writing. Cos k alpha plus sin k alpha multiplied by cos alpha plus sin alpha. So first row with first column, cos alpha plus sin alpha. This is first multiplication plus this second value with the second value of the column. So root 2 sin k alpha into minus root 2 sin alpha. So I am directly writing because root 2 and root 2 is 2. If you multiply root 2 and root 2, that will be 2. And negative, just put a negative sign here. So 2 sin alpha sin k alpha. Okay. Now second one I am writing just below it because there is not enough space. Now the first row with the second column. That is, I am multiplying cos k alpha plus sin k alpha with root 2 sin alpha. So root 2 sin alpha into cos k alpha plus sin k alpha. You can always use k as m also. Plus, now root 2 sin k alpha multiplied by cos alpha minus sin alpha. Root 2 sin k alpha multiplied by cos alpha minus sin alpha. That is, the second value of the first row of the first matrix multiplied by the second value of the second column. So cos alpha minus sin alpha. Now we are taking the second row of the a raised k and first column of a raised 1. So minus 2 sin k alpha multiplied by cos alpha plus sin alpha. Plus Now cos k alpha minus sin k alpha need to be multiplied with minus root 2 sin alpha. So I am purposefully placing a sign negative here, root 2 here, and sin alpha will be multiplied by cos k alpha minus sin k alpha, right? Now this row, see, this is already done. Okay. Please remember, second row with the first column we have multiplied. And now second one. So minus is root 2 is 2 sin alpha sin k alpha. Second row, this minus 2 root 2 is 2 sin k alpha sin alpha. And then the second one is cos k alpha minus sin k alpha into cos alpha minus sin alpha. Cos k alpha minus sin alpha. Okay. Now we need to just multiply and use the trigonometric identity, relation, and equality and put the value here. First one I am writing. We are multiplying each and every element, and then I'll try to show you few of these entries and what it comes. Okay. So most of the thing you know about this, you need to know the what is cos A cos B plus cos A sin A sin B, like this, cos A sin B minus sin A cos B. All these you must know before actually attempting this question. So I'm multiplying now. See here, cos k alpha into cos alpha, and then cos k alpha into sin alpha, then sin k alpha and cos alpha, and then sin k alpha into sin alpha, sin k alpha into sin alpha, minus 2 sin alpha sin k alpha. But you see here, sin k alpha and sin alpha is already there. So sin k alpha minus 2 sin alpha sin k alpha is equal to minus of sin alpha sin k alpha. These two we are taking and we are subtracting it. Let us subtract it. So what do we get? Sin alpha sin k alpha negative. Okay. So we need to rearrange it. It's so that we can use the formula here. So there can be some cos A plus B, there can be some sin A plus B kind of formula. Okay. So cos A cos B plus sin A sin B we have, because cos k alpha and cos alpha is there. Do we have sin k alpha? Yes, we have cos k alpha, cos alpha, and this one we are taking minus sin k alpha sin alpha. So it is cos A cos B minus sin A sin B. Here we have, so cos k alpha sin alpha, that is cos A sin B plus sin A cos B formula. Okay. So what do we get? The first one is cos A minus B, A plus B, sorry. And the second one is sin A plus B. So this is sin A plus B sin k alpha plus alpha. This one is cos A cos B minus sin A sin B is cos A plus B. Just write cos k alpha plus alpha. So this is just the first entry. This is the first entry, okay? We have to do it for all the 4 entries, and depending upon the formula and the expressions, we have to devise the k plus 1 wherever n is there. Okay, now let's do the second entry of the first row. So I'm just saying that if k alpha plus alpha can be written as k plus 1 alpha. Alpha you take common. So what do we need? Excuse me. K, what do we need? We need, wherever k is there, we need k plus 1 alpha. Wherever there is k, we need k plus 1. And we got it. See, k plus, the first entry of the matrix is cos k plus 1 alpha and sin k plus 1 alpha, that we got. And same thing you have to do for every other entry. Let us take the one more entry till we have enough space. So I am taking this one. So root 2 Sine alpha. There is, what you can do is you can take root 2 common, because if you have root 2, you will not be able to use the expression and the equalities or the formula in what we have seen earlier in our trigonometry discussion. So what we will do here is we will take root 2 common here to make it easier. So just assume that root 2 is already there. Now multiplying the inside ones. So this we get sine alpha. Now multiply each and every element. Sine alpha cos k alpha, sine alpha cos k alpha, and sine alpha sin k alpha, sin k alpha, plus sin k alpha cos alpha, sin k alpha cos alpha, minus sin k alpha and sin alpha, sin k alpha and sin alpha. Now you see these two are common, so just cancel it out. What do you get? Sine, this is cos A sin B plus sin A cos B. And what was that? It is actually sin A plus B. You can say sin A cos B plus cos A sin B. It is sin A plus B. So sin k alpha plus alpha, sin k plus 1 alpha. Root 2 is already there. So what do you get? Root 2 sin n alpha, that is root 2 sin k alpha, we assume it to be true. Now we got root 2 sin k plus 1 alpha. So the first one was this one. The second one entry is this one, and which we wanted. So the third and fourth entry, we need to recheck, and I hope you will be able to solve it. First and secondary, I already told you. It was cos and root 2, but this minus root 2, this one minus root 2 sin k plus 1 alpha, and cos m1 plus this k plus 1 alpha and minus sin k plus 1 alpha, you have to do by yourself. This is for your reference. So 2 I have done, 2 you have to do. Okay. I hope you have got the idea, because I told you how to do it. Now A is this. Then use the principle of mathematical induction to show A raised n is this matrix. We'll use it. We use the concept of mathematical induction. The first one is this. If you put n as 1, what do you get? A raised 1. So in A raised n, just put n as 1. So 1, 1. I'm writing other ones. 1, 1, 1. And then we have 0, 0, 1. Okay. N plus 1 by 2. 1, 1 plus 1 by 2. That is 2 by 2. That is 1. So what do you get? It is 1. So this one is exactly similar to A. And A is nothing but A raised to the power 1. Now the second step is, we assume that it is true for any k. You can also call it as m, but I am calling it as k. For any k it is true. That is 1 k, k plus 1 by 2, and this is 0, 1 k, 0, 0, 1. Right? Now the third step is that if assuming that it is true for A raised k, it must be true for A raised k plus 1. If we are able to show it for A raised k plus 1, then it is true for every integer n. A raised k plus 1, how do we write? A raised k into A raised 1. So wherever you see k here, the answer should be k plus 1. Everywhere k plus 1 should come. So now I am writing A raised 1 because I am multiplying A raised k with A raised 1. I am multiplying these two. This is simple matrix multiplication. So multiply 1 into 1 is 1, k into 0 is 0, k plus 1 by 2 into 0 is 0. So only 1 will remain. Now the first row with the second column, 1 into 1 is 1, k into 1 is k, and this into 0 is 0. First row with third column. So we have 1, 1, 1, so all has to be added, 1 plus k plus k plus k plus 1 by 2. This needs to be added. Now second row with the first column, 0, 1, 0, 1, 0, 0, 0, k into 0, 0, everything is 0. Now second row with the second column, 0, 1, 0, 0, 1, 1, 1, and k into 0 is 0. And now second row with the third column. So 0, 1, k has to be added because all ones are there in that column. So 1 plus k will be there. Now this row with this column, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, so only 0 will come. Again 0 into 1, 0, 0 into 1 and 1 into 0. So 0 will come. Now the third row with the last column, so 0 plus 1, that is going to be 1. Okay. Now you have already reached the step, because I wanted k plus 1 and we wanted k plus 1. So k, this is k, we got k plus 1. This is k, we got k plus 1. So only this one we need what? We need k plus, everywhere k plus 1 should be there. So we need k plus 1 and then k plus 1 plus 1, that is k plus 2 and divided by 2. This is what we get. If we solve this one and we get this one, we are already done. So let me solve this. 1 plus k into k plus 1 by 2. Now 1 plus k, you take common. 1 plus k by 2 will remain. So this is 1 plus k and this is 2 plus k by 2. So k plus 2 by 2. And what is this? This is what we wanted. Okay. This one is exactly similar to this one. So we have already proved that it is true for a raised k plus 1 if we assume that it is true for a raised k. This is the final answer, that this is true for every positive integer and for any k assumed to k plus 1. If BC are n-row square matrix and if A is equal to BC, BC equals CB, C square equals null matrix 0, then show that every n belongs to capital N, A raised n plus 1 is given by this expression. N-row square matrix means if it is having n rows, it will also have n columns because it is a square matrix. So what is given in the question is this one. We'll use the mathematical induction here and try to resolve the issue so that we get, first let us start with n equals 1. Wherever you have n, put 1. So left hand side, if you put n as 1, it will be a 1 plus 1 a square, n is 1. Right hand side, b raised n is 1, and then b plus n will be 1, 1 plus 1 is 2, so b plus 2c. A square is b into b plus 2c. Let us see what is a square actually coming. Because a square is nothing but a dot a. A is given b plus c. So we can multiply b plus c and b plus c because a into a. Multiply each and every element, b into b, then b into c, then c into b, then c into c. C square. This is b square. Now, BC plus CB is already given to be equal in the question, and C square is also given as 0. So BC and CB are equal. BC plus CB, CB can be written as BC. BC plus BC is 2BC. So you have B square plus 2BC, and C square is already 0. So just take C square as 0 because it is given in the question. So it is already given, so we can just take b common from here. In b square plus 2bc, I am taking b common. What do you get? B plus 2c. And this is exactly similar to right hand side of a square. See here. So for n equals 1, we have proved it. For n equals 1, it is true. Now the next step is we assume it to be true for n equals k. So n equals k. So wherever n is there, just put n k. So a raised k plus 1, b raised k, and b plus k plus 1, c. We assume this to be true. And if it is true, we need to show that everywhere when k is k plus 1, it is also true. If it is k is true, k plus 1 is true, then it is true for any value which you choose. So we will try to do it for n equals k plus 1. Okay. So in place of n, I am writing k plus 1. So I am writing k plus 1. So a raised, in place of k plus 1, so plus 1 is already there. So a raised k plus 2. K plus 1 is, k plus 1 plus 1 is k plus 2. So k plus 2 is there, is equal to b raise, n is k plus 1, we are writing k plus 1. Then we inside have capital B plus n, I'm writing k plus 1. So k plus 1 is k plus 2 into c, right? Now this a raise k plus 2 can be written as a raise k plus 1 into a raise 1, because if you add the power it will be k plus 2 only. A raise k plus 1 is already there. A raise 1 is already there with us. How do we get a raise 1? When we put n as 0. If I put n as 0, I will get a raise 1. So right hand side also you have to put n equals 0. So b raise 0, and then we have b plus n is 0, so it will be 1 only, so c. So b into b plus c. b raised 0 is already 1. Anything raised to the power 0 is 1. So a is bc. A raised 1. Essentially what I am trying to suggest here is a raised power 1 we need to find out. In place of n, if we put n as 0, then we get a raised power 1. So right hand side also n has to be put 0. Essentially we get b plus c. So a raised k plus 1 I have already written, and a raised 1 I am writing it as b plus c. This I am writing again, b raised k. A raised k plus 1 is what? B raised k and b plus a plus 1 into c. This is a raised k plus 1, and a raised 1 is, as I just suggested, it is b plus c. Just write b plus c. So we already come till here. I will directly multiply it. B multiplied with b raised k plus 1, bk plus 1, k plus 1 plus the power is added, bk plus 2 will be there. This is k plus 1, b raised k, and b raised k into b into c, or c into b. Because bc, cb are same, that is why I am writing interchangeably. Now coming to c, this is b raised k and c, and then we have this one, the last one, which is k plus 1 b raised k, and c into c is c square. K plus 1 b raised k, c into c is c square, but c square is already given 0. So you just leave this because it is 0. What do you get? bk plus 2. Now what do we want to have? We need a raise. Let me tell you again, it is n should be kept as k plus 1. So we need a raised k plus 2. This has to be equal to b raised, in place of n write k plus 1. Inside just go there, b will remain like this, n will be k plus 1. So k plus 1 is 2, and then c. This is what we wanted. Finally, whatever we do here, whichever arrangement we do, we need b, this above element which I just told you. B raised k plus 2, this is already 0. Now I am taking this is b raised k dot b. So this is essentially equal to b raised k plus 1. Okay. So b raised k plus 1 and c we can take common. Why? Because bc and cb are same. So I am just taking this c b k plus 1 or b k plus 1 c I am taking common. So k plus 1 remain here and 1 from here. So k plus 2 will be there. K plus 2. And now we'll take b raised k plus 1 common from all these two. So I am taking b raised k plus 1 common. What is remaining here? Only b. This already we have taken b raised k plus 1. So only k plus 2 into c will remain. So what do we get? Remember, I told you a raised k plus 2 will be what? This is exactly similar to this one. So by principle of mathematical induction, it is proved. This question we'll take in the next discussion. Okay, thank you.